So what I'm going to do this evening is really, it's a very general talk about volcanoes, explain why we have volcanoes on the Earth, talk about the different kinds of eruptions and what causes those different kinds of eruptions. And then I'll talk about the management of volcanic risk, because one of the points about volcanology is it's a very practical, applied subject as well as an academic subject. And so the knowledge you get about volcanoes is used to provide support for communities who are threatened by volcanic eruptions. So I'll be talking about the management of volcanic risk, and I'll be using the Soufriere Hills volcano in the Eastern Caribbean, which had a big eruption which started about 30 years ago, and I was very much involved in that eruption, and I'll tell you the story of that. Okay, just a little bit about what's going on around the world. There's probably around 40 or 50 eruptions every year on the Earth. And just some recent examples. This is the famous volcano in Java, Krakatoa, in December 2018. And the first thing you can see is that volcanoes are very awesome and beautiful phenomena. So they're probably about the most dynamic thing that you can imagine to demonstrate we live on a dynamic planet. But they also, of course, have a bad side to them, and this is the same eruption. This is an aerial photograph of the volcano of Krakatoa. You can see the crater, and there's a little island, and during that eruption, there was a big landslide. Part of the volcano fell into the sea, and it pushed a tsunami which went to the coast of Java and did quite a lot of damage. And there were quite a few deaths associated with that eruption. So volcanoes are wonderful things to watch and see, but they've also got this threatening side. This is another example. This is 2005 in Chile, Coroncoy volcano, and this is an explosion, and you can see this spectacular lightning that occurs around the explosion cloud. So again, another example of the sort of awesome beauty of volcanoes. And this is a volcano in the Tonga Islands called Hunga, which had a world-beating eruption. This is the cloud from a satellite image, which is, you can see it's 500 kilometers diameter. So it's the size of a hurricane. And it's an enormous explosion. It also produced these are some of the little blue areas, are some of the little islands in the Tonga island chain. And it also produced a huge tsunami which swept over some of the islands and again did a lot of damage. But there's just, again, the sheer size of these eruptions. And this is the world-beating volcano because this cloud you can see from space got up to 57 kilometers high above the volcano. It was absolutely enormous. And that's the greatest height that we know about from any historic eruption. And here we go. And this is the Fagradalsfjall. I'm sure, hope there's no Icelanders in the audience because I've almost certainly mispronounced it. But this is the volcano that's been erupting at the moment. You've probably seen on the news in the Reykjanes Peninsula south of Reykjavik. And there have been a whole series of little eruptions in this area, and they're still ongoing. There's probably going to be some more. Again, really quite spectacular. But of course, as you probably know, some of these lavas have gone into the town of Grynsvik and have caused some damage to the town. So there are these two sides of volcanoes, that if you like, the beauty, the good and the bad. And then, of course, another dimension of volcanoes is that some historic eruptions and eruptions in the geological record have been truly enormous. And so just a little word about how big volcanoes can be. And there's some examples here. This is one of the biggest eruption of the 20th century, is Mount Pinatubo in 1991. And it erupted an astonishingly 5 cubic kilometers of magma. That's an enormous amount. You imagine a cube 1 by 1 by 1 kilometer, and there were 5 of those. And when those erupted, the volcano fell back into the earth, into the hole that had been vacated, and formed what's called a caldera, or a big explosion crater a few kilometers across. So that's the biggest eruption of the 20th century. Up on the left is the biggest historic eruption, called Tambora in Indonesia in 1815, and that's the biggest, and that erupted that's about the biggest eruption of the last 1,000 years, and it erupted 45 cubic kilometers of material, and it formed a deep crater about 6 kilometers diameter. So that's the biggest of the last 1,000 years. Well, the biggest of the last 100,000 years in Earth history is a true giant. It's the volcano called Toba in Sumatra, and that had an eruption 74,000 years ago, and this erupted 2,800 cubic kilometers, and it formed the largest volcanic crater on Earth, the Toba caldera, which is a crater 100 kilometers in one direction and 30 kilometers in the other. And this Tambora, remember the biggest eruption on Earth in the last 1,000 years, I've just put it on the same scale, 6 kilometers diameter, just to compare it with how big Lake Toba is. I mean, it's truly an astonishing event. And some people have claimed that this eruption was so big it might have had an impact on human evolution. Maybe in the question times we can talk about that some more. So eruptions in the geological record can be truly enormous. Well, so the first question I want to answer is, why do we have volcanoes on the Earth at all? And the answer to that, I'm sure everybody's familiar with the structure of the Earth, the crust, the mantle, and the metal core. And why we have volcanoes is that the inside of the planet is very hot. Now, I think I made this talk for a talk in Geneva, so that's why it's Geneva. I should have changed this to Martley, shouldn't I? But it's true here as well as in Geneva that if you go about 100 kilometers down beneath here, we're going to be at temperatures of 1,200 degrees centigrade. So the inside of the Earth is extremely hot. Now it's solid, and it's really important to realize there isn't a big lake of molten rock down there. It's completely solid, the inside of the Earth, the mantle. Until you get to the core, we won't worry about that for the moment. Center of the Earth's at 5,200 degrees centigrade, but it's very hot down there. And the main thing is that it's so hot that it's not very far off the melting temperature of the material. It's below the melting temperature. It's a solid, but it doesn't take very much to make the inside of the Earth melt. And what I'm going to show you is that the main way that this melting happens is not to do with heating anything. We're used to lighting a candle and the wax melts, or heating up something and it melts. But that's not how melting occurs in the Earth. And there's 2 main mechanisms which I'll now talk about. And before that, I'll just, Kay mentioned that I'm sure this will be a very well-informed audience who will know about plate tectonics and the way the Earth is divided up into plates. And some of these plates are pulling apart, as they are in the South American plate and the African plate are pulling apart, and we get most of the world's volcanoes along the plate boundaries. So we get them where the plates are pulling apart, and they get them where the plates are pushing together, like South America and Chile, so where the plates are colliding. So most volcanoes on the Earth are associated with plate boundaries. Now, of course, the plates are the very cold outer layer of the Earth. The first, if you like, 50 kilometers or so is cold, and it's solid cold rock. And so they're strong, and the plates are brittle, and they break apart, and they pull apart, and they push together. So why should we get, if the inside is molten, and here's just the make that point that most volcanoes are on plate boundaries. There doesn't look like, if you go to the Mid-Atlantic Ridge, there are not many triangles, but there actually, if you went in a submarine and mapped them all, there would be hundreds of volcanoes there. It's just that we haven't gone to see them and name them because they're on the rift. So there's also a huge amount of volcanoes along the Mid-Atlantic Ridge. And you can see when you get to Iceland, there's loads of them. Well, why do we get volcanoes? Well, as I say, in the classic section of plates, going through plates, where there's places where the plates pull apart, the ocean ridges, and then there's the places where the plates push together, and one plate goes down into the area, they collide, and one of the plates sinks back into the interior of the Earth. And this is the sort of evidence, if you look on the left-hand side, this is an image using seismic tomography, which is just like a CT scan you get when you go to a hospital, of the inside. Where the blue colours are, it's cold. Where the orangey colours are, it's warm. And here you can see, by sending seismic waves through the Earth, you can actually image the plate going down. And all the little black dots are all the earthquakes, where the plate going down is scraping along the inside, and we get lots of little earthquakes. So you can see the plates these days. And then if you go to the ocean ridges where the plates are going apart, you can also image them. And so again, the blue is cold rock, and the warm colours, the oranges and yellows, are warm material. So we can image the plates nowadays. And the main thing is that where the plates pull apart, the hot rocks from inside move upwards as the plates move apart. So that you can imagine them pulling apart and the stuff goes up. And so what happens is the material going up here changes pressure. It reduces pressure and it melts because the pressure's gone down. It's not because we've heated anything up, it's simply that we've got something under pressure. Well, the melting temperature, it's below the melting temperature. And then if the pressure goes down, it just spontaneously melts. And that's why we have volcanoes all the way along the ocean ridges, and we get volcanoes in Iceland. It's just the change of pressure. Now, why do we get volcanoes where they collide together? One plate goes down, we've got a plate here, and that's got a simple explanation as well. At the ocean ridges, underneath the floor, the hot volcanic rocks interact with seawater, and the plate absorbs a lot of seawater. Now, the other mechanism that works in the Earth is the same reason that today, the salt gritters are out, because they want to make the ice melt on the roads. And the way that works is you put salt on the road and the melting temperature of ice goes down. So putting salt onto ice makes it melt. So adding a chemical to something else can make it melt. Now, water reduces the melting temperature of the Earth's interior by hundreds and hundreds of degrees centigrade. So what happens is the seawater is taken on this plate, it goes down, and as it gets hotter, that water comes off, and just like the salt makes the ice melt, the water makes the inside of the Earth melt, and that melt then comes up to the surface, And we get volcanoes in Chile and Mount St. Helens and so forth, and Krakatoa. So all those volcanoes are caused by seawater being pushed down by the plate into the hot interior, and that makes it melt. So those are the two mechanisms. This is just what the firstly, this is a rock. This is a bit of peridotite. That's what the inside of. That's 90% of our planet is made of this stuff on the left, and that stuff is just solid. And what this is what's the melting temperature? Just think of this. This is temperature and depth or pressure. This is just the melting temperature, and we can see that if we take that green blob down at depth and we take it to the Earth's surface, the pressure goes down, it crosses the melting temperature curve and the rocks melt. If we add some water to that green dot, it's normally got very little water, and we add some water from the sea floor because we've pushed the plate down, then it goes across there and it spontaneously melts. So in other words, the melting temperature goes from here to here, the temperature, and so adding water makes the rocks melt. So that's essentially why we have the volcanoes. Now, the way it melts, if we take a bit of that rock, peridotite, which has got olivine and pyroxene in it, and we start to melt it, what happens is little bits of melt form around the crystals, and they have geometries like this. So it's like a sponge. It's got the little crystals have got melt, and as the plate moves apart, this sponge is squeezed, and the melt that forms squeezes out and separates and then comes to the Earth's surface. So that's really why we have volcanoes. And just to show you from the ridges some of the processes, here's some pillow lavas from the mid-ocean ridges. This is the melt that's been squeezed out of the Earth's mantle, formed by this process. And here is the reason we get volcanoes where the plates collide. This pillow lava heats up the seawater, and we get something called a black smoker, a vent, a hydrothermal vent or a fumarole on the ocean floor, which can discharge at 350 degrees centigrade. And that's the interaction of the volcano and the seawater squirting out these black smokers. Okay, so that's why we get volcanoes. Let's just have a little look at how many volcanoes there are on Earth. We reckon there's about 551 historically active volcanoes on the planet. There's probably a lot more. And at the moment, the inventory is about 1,500 volcanoes, which we think is likely still active. So only a third of the Earth's active volcanoes have actually erupted with an historical record. Now, what that means is very interesting, because it turns out that about every 2 years, there's a volcano that erupts on the Earth which has never had an historical eruption before. And if it erupts where a lot of people live, those people know nothing about volcanoes. If you're somebody in Japan living near to volcanoes, you know something about them and you do things. But every 2 years, there's an eruption somewhere on the Earth with no historical records, and sometimes that happens near where a lot of people live. So that's a bit of a problem. Another thing about volcanoes, I'll talk about it a bit more later. The very big eruptions affect global climate. Those big craters I showed you put a lot of pollution into the atmosphere, and I'll mention that later. And because of population growth and infrastructure, the Earth is becoming much more vulnerable to volcanic eruptions. So it's not just that we have an eruption every 2 years that hasn't had an historical record. We also have this problem that the Earth's population is growing. Okay, why do volcanoes explode? Well, I mentioned before that all volcanoes represent molten rock, and deep in the Earth, particularly where the plates go down, we've taken a lot of seawater there, which is the main volcanic gas, and the molten rock dissolves the seawater just like a fizzy drink dissolves carbon dioxide under pressure. And so when the magma comes up out of the Earth's interior, it's got water in it and other gases like carbon dioxide. And when it comes up to the low pressure of the Earth's environment, lots of little bubbles form, and lots of bubbles cause it to explode. And it explodes in a very, very violent way. And you can see here in this picture a cloud from a volcano in Chile, which is going up to about 30 kilometers high in the atmosphere because it's such a powerful process. I mean, it's really well the same as if you get some champagne or Coke, and you rattle the tin and then you open it up. Of course, you get a great big spurt of foam in your face. And that's really, it's the same principle. It's just the energy is phenomenally much greater. And in this case, in a volcano, the stuff coming out of the volcano will be going at about 1,000 kilometers per hour. So enormous speeds and energies. So that's why we get volcanic explosions. And this is just an example. Mount St. Helens in 1980, erupting, and it produces this big cloud in the sky. This is just some experiments that we did to simulate this in the laboratory. But I just want to get over a sense of just how violent these are. This, in Mount St. Helens in 1980, this eruption erupted 10,000 cubic meters per second. So this room would be 10 by 100. But I wouldn't be surprised if this room was of the order of 10,000, a few thousand cubic meters. And every second, the volcano was spewing out that volume during this eruption. And there's just so much energy in there that that's why it's so energetic. Okay, let's now, before I show you this, I'm just going to show you some film of some explosions from volcanoes. This is from the Soufriere Hills. Just give you a little bit about background. And we're moving now into the applied side of the subject. So I've moved, sort of going through the more academic stuff, but now we're going more into the applied side. So I got some money for Bristol University to coordinate a global project to create films for communities around volcanoes around the world, and worked with people internationally. And we've produced 14 films in 9 different languages. And these are all free on the web. You can get them from Vimeo, and you can download these films I'm going to show you and watch them. And then I'm going to hope.
Magma is the molten rock beneath volcanoes. It's filled with gas that expands as it erupts, like the bubbles in a fizzy drink when a bottle is opened. In explosive eruptions, this tears the magma apart and shatters solid rock. These explosions form fragments of magma and rock, which range in size from a fine dust to boulders the size of cars. The finest material, the size of a grain of sand or smaller, is called volcanic ash. Rocks thrown from a volcanic vent are sometimes called volcanic bombs. The biggest rocks fall to the ground close to the volcano, where they can cause deaths, injuries and damage. Large rocks can punch through roofs and sometimes set buildings on fire. The falling of smaller rocks is noisy, like a heavy hailstorm. Towering clouds of rocks, ash and gas are thrust above volcanoes during explosive eruptions. These volcanic clouds often reach heights of many kilometres, and in the largest eruptions may reach tens of kilometres high, well into the height that aircraft fly. The ash clouds are blown by the wind tens to hundreds of kilometres from the volcano. The time taken to reach these distances depends on the speed of the wind. Day can turn to night when the thick, dense ash clouds block out the sun. As the volcanic clouds drift downwind, the material within them gradually falls to the ground. The thickest deposits form closest to the volcano, where buildings and land can be buried. Fine ash is transported further from the volcano, and the deposits normally become thinner. The finest ash can remain airborne for thousands of kilometres. Volcanic ash is quite different to the ash produced in a fire. It's made up of tiny, sharp fragments, making it extremely rough and abrasive, able to badly scratch car windscreens, for example. Volcanic ash can be harmful to people, animals, and the environment. Lands can be buried, roofs can collapse. Transportation, water resources, wastewater systems, power supplies, and communication systems can be disrupted. Crops destroyed, and livestock killed. In small eruptions, ash can prove to be a nuisance by disrupting everyday life. Scientists can study eruptions and wind patterns to provide warnings of the spread of volcanic ash. Authorities will advise the best course of action. This may include evacuation of areas close to the volcano and measures to protect your property and yourself. Over time, communities living near regularly erupting volcanoes can develop good coping mechanisms for living with the hazards. And in the long term, volcanic ash can improve the fertility of the land.
Now, did anybody recognise that voice? That's Ian Stewart, who, of course, has done a lot of work with the BBC and so forth, and Ian very generously agreed to overvoice that film. And as I say, you can download all these. I'm going to show another film in a bit. You can download these from the net. Okay, one other phenomena to tell you about. You've seen in the film and so far that big explosions put stuff high in the atmosphere. They don't always do that. Sometimes the stuff comes out of the volcano, and instead of going into the atmosphere, under gravity it collapses and flows along the ground in something we call a pyroclastic flow. Now, this is something you definitely don't want to be involved with, because it's hundreds of degrees centigrade, and these flows can go at 100, 200, 300 kilometers per hour. They are the major killers of people in volcanic eruptions. And this is some pictures from Mount St. Helens. Again, a little experiment we did to simulate this in the laboratory. But that's the idea. It comes up and it flows down. So I'm going to show you another of our films so that you see, and again, this is Ian. Can everybody hear it, okay?
Pyroclastic flows are one of the most deadly of volcanic hazards. They are rapidly moving avalanches of hot rock, dust and gas that flow down the sides of a volcano into surrounding valleys. They can climb up and over ridges and high ground. They are dangerous because they flow much faster than a person can run, and often faster than a car. So for those in their path, there's little chance of escape. What makes them especially lethal and devastating is that they're extremely hot. During the day they appear grey and ashy, and at night they can be seen glowing red hot. They destroy and burn anything in their way. Death or severe injury is certain for those caught by the pyroclastic flow. There are two main ways pyroclastic flows may form. Sometimes a volcano explodes and forms a fountain of hot pulverized rock and gas that first rapidly rises into the sky and falls back, forming pyroclastic flows which race down the sides of the volcano. Other times, instead of an explosion, sticky lava oozes out of the volcano and piles up around the summit. Pyroclastic flows can then form by parts of the lava collapsing. Although pyroclastic flows normally move down valleys, extremely hot, fast-moving, billowing clouds form above them, which can spill out of valleys. This means that even people on high ground are not safe. Pyroclastic flows normally travel to distances of 5 to 10 kilometres from the volcano's summit, but in the biggest eruptions, they reach much more than 20 kilometres. Volcanoes that haven't erupted for many decades or even centuries may appear peaceful, but when they awaken, the eruptions are often very large and explosive. Scientists can detect that a volcano is reawakening and are able to provide some warning or advice to evacuate, which is the only protection from pyroclastic flows.
So, okay, so you've seen two of the why we need to understand volcanoes from a practical point of view to protect communities around volcanoes. And so often one of the questions one often gets is, can you predict the volcanoes? Can you give early warnings? And the answer is, generally you can't predict, but you can forecast, like the weather. And so you can give some sort of probability that an eruption is going to happen and give people warning, just like you would give a weather warning. So prediction's pretty difficult. Very occasionally, you can see something in a signal, and this is a technical diagram, but this is time on this axis, and this is the frequency of seismic waves created by the volcano. And there are certain tones, just like musical notes, that the volcano gives off, which change their frequency systematically. So where you see these bright spots, these are frequencies which are dominant. And you can see in this case that this frequency, this is in hertz, increases just before an explosion. So in this case, you have about 20 minutes warning if you see this signal. Not very long, I'm afraid. And this is the reason, of course, that you want to be able to forecast and warn people. This is one of the greatest tragedies in volcanic history, the 1902 eruption of Mount Pelée, when an entire town of Saint-Pierre, 29,000 people died. And it says when political priorities take precedence over public concerns, this might be a familiar story. There was an election going on in Saint-Pierre in May, and some of the engineers and a doctor in Saint-Pierre warned the politicians that they should cancel the election because they were worried because there was a lot of activity at this volcano of Mont Pelée. And the politicians delayed and delayed and delayed. And of course, on May the 8th, I think it was, 1902, a huge pyroclastic flow, just like you saw in the film, swept through the town. And because it was going at 300 kilometers per hour, this is what was left of the town. Virtually everybody lost their lives. So it's one of the great tragedies of volcanic history. So this is the reason, of course. Another example, this is the town of Almero in Colombia in 1985. And this is a bit different because the volcano had a glacier on it, and when the volcano erupted, the glacier melted very quickly, and a huge surge of water went down the valleys, turned into mud, and buried the town of Almero with 23,000 deaths. And this was a problem, again, of communication. The warnings had gone out, but they hadn't reached the village in time. So a lot of volcanic tragedies are related as much to human error or human issues as they are to the volcano. So that's a little bit of background about why we should be worried. Now, in 1995 to 2010, the Soufrière Hills volcano on the island of Montserrat in the Caribbean erupted, and I was very heavily involved in running the observatory and monitoring the volcano. It's a British dependent territory. And so I'm going to tell you a little bit about some of the work we did there. It's an island just off Antigua, and it's a very interesting island. At the time before the eruption, it had never had an historic eruption. No historic eruptions. The people had no idea, although scientists knew that it was an active volcano, the local people didn't. And there were about 12,000 people living on the island, and this volcano is in the south of the island, Soufrière Hills. So that's the background. This is just a snapshot of what happened during that eruption. It erupted for 15 years. And just a little bit of a snapshot to just give you a flavor. Here's the volcano, which was sometimes producing a lava, and sometimes producing explosions, and sometimes producing pyroclastic flows. That's the capital of Plymouth, which, just like Pompeii and Vesuvius, was buried by pyroclastic flows during the eruption. This picture tells you something. This is the new hospital that the British government built on the island in 1993, just been opened when the eruption started, even though there was a report from scientists saying that the infrastructure should be built in the north of the island, because that was further from the volcano. This was ignored, and the new hospital from British taxpayers was built, and that's what it looked like after being buried by pyroclastic flows. And this is something about communities. Just a message. This is a guy who's moving his house away from the volcano. And it, of course, shows you about the resilience of communities and innovation under threat. So this bloke didn't want his house destroyed, so he just put it on a lorry and took it to the north of the island. So a bit of enterprise. Okay. This is, again, just to give you a snapshot, but this is every little dot on the little map is an earthquake that took place on the island. And we could tell a lot from these earthquakes. We could find from the earthquakes how deep they were. And so we found the depth to the body of magma. Remember, the volcanoes are underlain by molten rock. And so using the earthquakes and other techniques, we could tell that that magma chamber was at about 5 kilometers depth. And we could do something called ground deformation. This is one of my PhDs from Bristol University. I had a team working out there. And what she's doing is she's got a mirror on the volcano, and she's sending laser light to the mirror and bouncing it back. And the reason she's doing that is during volcanic eruptions, the magma chamber puts pressure on the earth and the ground lifts up. That's shown in this little diagram here. Here's the magma chamber, and before an eruption it swells, and the ground is pushed up and raised up, and you can measure that. So you can also use this to help you warn about the volcanoes. You can use GPS and satellite images and all sorts of ways nowadays of measuring how a volcano swells before it erupts. And this is some of the pattern. This is a very noisy diagram. I apologize for that, but just try and take you through it. This is the date, 1995, so we're coming along here. This is 2013. The top diagram shows you the number of earthquakes per day. The middle diagram shows you the uplift of the ground and the subsidence of the ground from GPS signals. And this shows you the amount of sulfur coming out of the volcano during the period. And the point about this is, look at this one, just to take this one. These are just GPS positions. So it's just a GPS station which tells you how much the ground's going up or down. And so when it's red, the volcano is very active. And when it's green, it's not very active. When it's active, you can see the ground is going down. And that's because stuff's erupting out of the ground, and underground it's collapsing. So the ground surface goes down. Before an eruption, you can see that these dots are going up. So the ground is lifting up. And then it erupts and the ground goes down. And so the volcano is behaving in a very sort of predictable way. So we have this sort of fantastic data that we can use. So that's a little bit about how you forecast or how you use that information. That information, when the ground's going up, you're more worried. When the ground's going down, you're less worried about the volcano. Now, during this, we developed, and this is really the last bit of the story, or the final bits of the story, we had a team of scientists from the Caribbean and from the University of the West Indies, from the British Geological Survey, and quite a big group from my research team at Bristol working on the volcano. And basically, we had to create maps to advise the local government about which parts of the island were safe and which parts were dangerous. And this is always a bit of a judgment, because if you live in the red area, you have to move your house and evacuate. If you live in the yellow area, you're okay. You can carry on living in your house or running your business. So where that line goes is a very critical matter. So just imagine that you are in the house there and your neighbour is in the house the other side. And there's nowhere on Montserrat where that isn't true. So if you live in the red zone, you say, well, they're only living 100 metres away, aren't they? Why can't they? They can stay. Why do I have to evacuate? And so if the government said, OK, that's a reasonable point, let's put the line there. Well, the same problem arises. There's another house. And sooner or later, you're going to be at the volcano with that logic. So basically, that means that you have very tough decisions. The government has very tough decisions. And just like the COVID crisis, the advice of scientists to the governor of what's safe and what's not safe is a very critical judgment. Do we have lockdown or we don't have lockdown? That sort of thing. It's a black and white thing for something which is a gradient, of course, because the further you are from the volcano, broadly, the safer you are. And there's no really, nature doesn't know there's a line there. So that leads to work, and this is us doing this work. We formed a group which did a risk assessment. And these are colleagues from the University of the West Indies, the British Geological Survey, and so forth. And we developed some techniques which were, I think, actually very novel in the sense that this had never been tried before, but we used to try and quantify risk. And the sort of question we wanted to ask was, what's the chance that a village 6 kilometres northwest of the volcano will be buried by a pyroclastic flow? If the chance is very high, the people should be evacuated. If it's very low, maybe they can carry on staying. But how low does it have to get before you make that decision? So that's what we did. And I'm not going to, you'll be relieved to know I'm not going to show you a pile of statistics, but what we did was we used all the scientific information and observations we had on the volcano, and we made assessments of what the probability was that this village would be inundated by a pyroclastic flow or not. It's a life and death decision. And we estimated the risk and the uncertainty. So this is a probability process, which is, again, just like weather forecasting. And this is the situation in July 2003 that we faced. Here's the volcano. That grey thing, that's the lava. And if it was at night, it would be bright red. And down this valley here, to the right, there was a village and an area with a few hundred people in it. And the lava had got so big, we were worried that it might collapse down this valley and form a pyroclastic flow which would go into this village. And so we did a risk assessment. We worked out the probability that that might happen. And on the basis of that, this area was evacuated, several hundred people. Now, you can just see, if you look at that, just to give you a flavour of it, of course, it might collapse and it might go to the left, and that would be fine. It wouldn't threaten the village at all, but it might fall down this valley, and that wouldn't be fine. So you have to sort of work out what's the chances of it going one way or the other way. That might be something you'd need to think about. And this is the valley. Here's the volcano. This is the valley, and these are the communities in this valley which we were concerned about. So we did this, and we ended up with something that I need to take you through in this sort of thing. We wanted to know the chances of it going down there. We wanted to know how many people lived in this area, in different areas, and we wanted to know how far you would have to move them in order for it to be safe. And then you'd have to present those results in some way that the governor of the island and the chief minister of the island could comprehend. And the way we did it was to show them a risk chart. And the way this works, and I'll take you through this because it's important to understand, this is the probability of an event that will have a certain number of deaths on that axis. And this is the number of deaths that event might develop. Now, if we didn't move the people, you can see the red curve, and this would be the sort of, that red curve, so the way to read this is, you can see it's 0.1. Well, that means that there's a 1 in 10 chance of more than 10 people dying if you keep the people in those areas. There's a 1 in 100 chance that we might get 20 or 30 people killed. So those are things. So we're dealing with, you leave the people there, you've got a good chance of a mass casualty event. And that's the reason. So when we showed them this red curve, then they said, oh, well, that's too high a risk, and we'll call the evacuation. Now, we then said, let's move the people from this area, but we'll leave them in this area too. And we'll redo the calculation, and that's the grey curve. And if we push them a bit further back still, that's the grey curve. So we've reduced the risk the mass casualty event by a factor of 100 by moving them further north and away from the trouble. Now, is that still acceptable? It doesn't say it's totally safe. Well, what we did was we then plotted the chance of death, annual chance of death, from either a hurricane or an earthquake in the Caribbean. If you live in the Caribbean, you live with the risk of being killed by a hurricane, and you live with the risk of being killed by an earthquake. It's a very small risk, but societally it's an acceptable risk. And so what we could show them was by moving people away, the risk would reduce to the same level of risk that you would accept by living in a Caribbean island. And they would say that that was okay. We don't have to evacuate the entire island. So that's the sort of chart we used, and of course we had to explain this to a governor and a chief minister and so forth. So that's what happened. July 2003, here's the big lava dome. It's just to give you a scale, that's about the height of Snowdon, so I guess, just about that. It's a big mass, goes up to about 1,000 meters high, and it's about 1,000 meters wide. It's a very steep, it's a huge mass of stuff. And what happened July 2003, next day, 13th of July, the entire lot collapsed down the east coast of the island into the sea away from the area that had been evacuated. The risk was there, the hazard was no longer there, the dome, all the lava was now in the sea, and so the evacuation was called off and all the people went back. So that's actually what happened. Right, how are we doing for... Okay, just a couple more topics and then I'll finish about the societal stuff. And I'll just finish with the impact of very large volcanic eruptions on climate. You've already seen that these big explosions can put a lot of stuff into the atmosphere, and a lot of it is sulfuric acid and little volcanic ash particles, and that bounces radiation back, solar radiation back into the sky. So every time you have a very big volcanic eruption, for the next few years, you have global cooling. Maybe that's, well, it's whether it's a good idea or not, that's what happens. But of course it creates, like any kind of climate change, it creates havoc. Last time this happened was from the Mount Pinatubo. Remember, right at the beginning, I said this was the biggest eruption of the 20th century in the Philippines. That's the size of the sky. I just want you to just look at this. This is 3 weeks after this eruption. This is a map of the world where all the pollution, the sulfur, is shown from a satellite image girdling the Earth. And in the next year or two, all this pollution spread over the entire Earth and gradually dissipated. And while it was in the atmosphere, the Earth's climate cooled down by about a degree. And this shows you why this is of great interest, not just for volcanoes, but for climate change. Look at this. This is the year after Pinatubo. It's a map of the world. And wherever you see a blue, it's colder than normal. Wherever you see it's reddish or orange, it's warmer than normal. You see, it's quite complicated. Most of the Earth cools down because the sun's radiations bounce back into the space. But bits of it, because of the way the climate works, bits of it actually become warmer. So it's quite complicated. And of course, that has effects on crops, agriculture, food supplies, etc. This is a global climate model, the sort of thing that predicts global warming, run on the same data. So volcanoes are very good tests of models of global climate change. So scientifically, their importance is way beyond volcanoes. It's an excellent test of whether the global models predicting global warming are any good or not. And you can judge for yourself. It's not a perfect match, but the patterns, the broad patterns, are very similar. So this was a very important eruption for climate scientists and atmospheric scientists in demonstrating that the models that they run, that sometimes the climate deniers poo-poo, actually don't do a bad job for real life experiments. So they're not just fiction. And they'll just go back to 1815 to tell the story of Tambora. Remember, this is the eruption I said was the biggest eruption on Earth in the last 1,000 years, just to remind you. And these are the estimated temperature in 1816. It was 2 degrees centigrade globally cooler than normal. And then over the next decade, it gradually warmed up again. But it created a 10-year perturbation of the climate. This is when Turner did all those wonderful, sort of sunset paintings because of the wonderful sunsets caused by this pollution. This is where Frankenstein was written by Mary Shelley because it was such a horrible winter in Switzerland when she went there with Lord Byron, and she was inspired to write Frankenstein. And this is the spike in the price of wheat in the USA when the crops failed in the summer of 1816 on the east coast of the United States, causing the farms, there was 3 frosts in June, July and August. And the crops, each time the farmers tried to plant the crops, so the wheat crop failed. This is an eruption in Indonesia. The price of wheat went up hugely, and a lot of the farmers from New England migrated west at that stage and abandoned the east coast of the United States. So an eruption in Indonesia had a global consequence. Okay, though the last question is, what would happen if there was one of these huge eruptions I talked about? Well, it doesn't look terribly good. This is the Earth after a model of the Earth after one of these gigantic eruptions. This is the summer and that's the winter. And you can see it's all blue, but look at the scale. If it's dark blue, this is minus 20 degrees cooler than normal globally. So that isn't very good. There would be, and the same in the summer. And you also might notice it's red in the poles. There's an atmospheric reason for that. And that's why the way the Earth's circulation works is why global warming creates melting in the northern hemisphere. So even with this big perturbation, we get actually warmer poles, which is weird. But the main point is it wouldn't be very good. It would be a sort of global catastrophe on a huge scale if we were to have one of these super eruptions. And this is ice cores data that we've been looking at from Antarctica. And the main thing is this is a spike in these ice cores. Whenever there's one of these big eruptions, it lays down some sulfuric acid and you can measure it. And that's the peak. And it's about something like 150 times bigger than Tambora was, the amount of sulfur that was put in Antarctica when the eruption occurred. So we can measure these things quite well. Okay, so I think that's it. I've sort of ended with global catastrophe. Sorry about that. And I'll finish that and happy to answer any questions.
Thank you very much. Right, yes.
Coming back to your political side of it, I mean, tourism is now a big problem because a lot of the countries that are potential hotspots are massive tourist spots as well.
Oh, yes, yes.
I was in Mauritius 4 or 5 years ago, and then also it's only volcanic, and the crater which you could visit was down to tourists. The lake at the bottom was turning acidic. They said, oh, it's not a problem. I said, well, something's happened. Oh, don't worry about it. You know. I thought it's normally just a water lake, and now it's an acidic lake. So clearly something is active.
Yes.
And linked to radiation as well.
Yeah.
People just, oh, don't worry about it. Nice to see you here.
Well, yeah, I mean, it's another volcano story, but you may remember in December 2019 that 22 tourists were killed on White Island in New Zealand. And that's really the same story. Had they done a proper risk assessment, they wouldn't have taken tourists to that island. It's very sad, but for really political, administrative. Now, New Zealand's a very sophisticated country in many ways, but they failed on that particular occasion, and I think it's because they didn't do a risk assessment.
Is that to say Costa Rica is Arenal is a tourist destination?
Sorry?
Arenal in Costa Rica is a tourist destination.
Yes.
You go and watch it.
Yeah. But again, if there are places you can go which is sort of reasonably safe, so it really requires a sort of proper risk assessment to decide whether it's safe for people to go or not.
What are your opinions about Yellowstone?
Yes. Well, I was almost going to mention that, but Yellowstone is one of these super volcanoes, and so you could see it wouldn't be very good if that happened on Earth. It will happen again. But the good news is that the return period of eruptions that size on the Earth is about 20,000 years. So we're okay. The chances that we will be alive or our grandchildren will be alive when something like this happens is very small.
We write that down.
Yeah. So, yeah, it's a very low probability, but of course, at low probability, it doesn't mean it can't happen. But it's about 20,000 years, so we should be all right.
When was the last one?
Well, Yellowstone that's globally, because there's quite a few of them. If you take Yellowstone, the return period's about 600,000 years for that volcano. So again, the chances of Yellowstone is extremely low.
It last happened about 600,000 years ago, didn't it?
Yes, it did. Yeah, yes, that's right. Well, that's true. Yes, that's actually correct. Yes.
So you were going to say something about what Toba might have done to humans.
Well, it's a theory, and it's quite controversial that Toba had such a big effect that it affected human evolution, and there's some evolutionary biologists who've argued that there's something called a human bottleneck. Now that I gather, this is not my field, but I gather that that's actually a legitimate idea, that there's a human bottleneck. In other words, there was a big, there was a point at which the human species from which we are descended was down to a population of a few thousand, and then it built up. And so this idea of a sort of evolutionary bottleneck. Now, you can date, it's a very crude technique, but by looking at DNA, you can tell something about rates of evolution. And people do that, and they work it out that that bottleneck probably occurred between 50 and 150,000 years ago. So the speculation is the Toba occurred in that period where this might have happened, but it's very broad. And so those people have put 2 and 2 and probably made 5, but they've speculated that Toba might have been the event which caused the human bottleneck. So that's the link. It's sort of fallen out of favour, to be honest. I don't think people think the dating is very convincing and so forth, but it's it's an idea that's been out there.
Thanks for an excellent and very well explained talk, Steve. As a mathematician, I was interested in this, what seems a very good idea to me, of putting probabilities on the possibility that plastic flow will go so far. Now, can you give me, without going into too much maths, perhaps some idea of how you worked out those probabilities?
Yes. We do it by a technique called expert elicitation, where you get a group of experts each expert has got to look at the evidence, the scientific evidence, the data, and which is not going to be complete, and it's going to be partial, and it's going to be biased and all that, and they make their subjective estimate of the probability. So you think it's 1 in 20, you think it's 1 in 25, you think it's 1 in 50, somebody else thinks it's 1 in 5. And then you pool those experts' estimates, and they're also asked to give their uncertainty. How confident are they that it's that number, or what do you think it could be? Could it be as much as this or as little as that? So each expert does that. So you then get I hope it's not too, you'll know, a Gaussian distribution or some sort of distribution. And furthermore, you weight the experts, you test them before they do this exercise to see how much they really know. And you then weight the experts according to how well they do in a calibration exercise. You then... No, you don't. You don't. So it's all anonymous, and you end up with a statistical distribution, which is the pooled distribution of all the experts. Now, this is now widely used in engineering and medicine and all sorts of things. And I think I told you in the pub about COVID. So that you can use this. Almost always, the pooled numbers perform better than the best expert in the group. And that's why it's now widely used in all sorts of applications. And I'll give you a little bit of this. This sort of what I did during COVID was with the guy I work with who really knows this stuff very well, a chap called Willie Aspinall. We volunteered to work on COVID-19 transmission because we thought that exactly the same techniques we used for predicting or forecasting of volcanic risk, we could apply to forecasting COVID risk. And to cut a long story short, we discovered that there was virtually no data on young children about their contacts. And so we went about using this technique, firstly to gather, we got about 35 primary schools in the UK. We got the teachers to observe the close contact relationships between children, which is, social distancing is basically based on that. If you're within a metre of somebody and they've got COVID, then there's quite a high risk you might catch it. And so there was no data on children, so we got teachers to help us work out how often and for what periods young children would be close to each other. And that data was then developed into a statistical model, and we made a prediction of what, firstly, how COVID would be transmitted in primary schools. And we use that data. So it's basically exactly the same as we're using on the same statistical techniques and assessments, but we applied it there. And then we assessed whether the government's strategy for primary schools was working or not. And of course, we discovered that it was pretty well useless. It made almost no difference. So the idea that a child would get COVID and then you'd send the whole class home for 2 weeks, which some of you may have experienced, was scientifically a completely flawed policy. What we were able to show was that when you had testing and you tested perhaps once or twice a week, was much better way, and you only sent home the child who tested positive, that made much more difference. That made a tangible difference. So, and it's really just about the risk of, it's a technical story in a way, but the fact is that you're most infectious before you get symptoms. And that's the key point, that if you have a child that gets COVID and they've got symptoms, they've already been more infectious the day or two before, and they've probably spread the disease around the class already. So there's no benefit, very little benefit of sending everybody home at that point, because it's already, the damage is done. There's a little bit, but very little. But if you can catch them by a test a couple of days early before they get symptoms and send them home, you've sent them home before they're more infectious, and therefore it works much better. So we applied this to so the techniques I'm showing you to COVID-19.
That's why you're not the government, you're just talking too much sense.
Well, we presented all the results to the Department of Education at the time, but it was sort of a bit too late, because I think we only got these. It took us a year or two to get to that point where we'd done the science, and then by that time everybody had realised it was a ridiculous policy. Sorry. Yes, except that it tells you what you'd do in a future crisis. You wouldn't do that. You wouldn't send all the kids home. Yes, yeah. Yeah.
Anyone else? I think it's probably tea time.
Yes.
So thank you very much.
Okay.